What's up, everyone? Welcome to our first online lecture of Math 18A College Algebra. First of all, I hope you guys are managing to stay healthy out there, staying inside, washing your hands, avoiding contact with people. It's been a pretty natural lifestyle for me in my room. Second of all, I hope you enjoyed your week off of class last week. I certainly did, but it's time for us to get back on the horse and pick up where we left off. So let's jump into today's lecture. So hopefully you'll remember from our last class meeting, we talked about the transformation of functions, and those were operations that you can do to a function to change what its graph looks like. And the exercise that I had you guys do was come to the board and perform some kind of a shift on the graph that I had drawn. So in this section, the algebra of functions, we want to talk about what kind of operations we can do to two different functions. So here's our definition. Given two functions f and g with overlapping domain. And so remember, your domain was the set of x values that you can plug in, right? X values we're allowed to plug into our functions. So if you have two different functions like f and g here, you need to have some parts of their domain to overlap. So let's say I had f of x equals x squared, and g of x is the square root of x. Well, remember, we can't square root negative numbers, so the domain of my g of x here has to be positive numbers only, and 0, right? But for f, my domain is all real numbers, so if I'm combining my two functions, I have to take the smaller one. I have to take this, the function g of x's domain, so that I'm allowed to plug in the same values into both functions. So once we have satisfied that, we can define the following operations. We can look at the sum of two functions, denoted like this, f plus g of x is equal to f of x plus g of x, kind of exactly what you would expect. And similarly, we can look at the difference of two functions, f minus g of x equals f of x minus g of x. So those two are pretty straightforward. We can also look at the product of two functions, which is denoted like this, fg of x just equals f of x times g of x. And I use the little dot here for multiplication, so I don't confuse it with my x's. Finally, we can look at the quotient of two functions. The quotient of f and g, denoted like this, f over g of x equals f of x divided by g of x. And here, we need our g of x to not be equal to 0, because remember, you're not allowed to divide by 0, and my g is in the denominator here, so g cannot be 0. So let's take a look at an example. Let's say I have f of x equals x squared minus 4, and g of x equals x squared plus x plus 3. And let's say we want to find f plus g of x and f minus g of x. So remember, f plus g of x works the way you think it does, f of x plus g of x. So all I need to do is take my functions, f of x and g of x, and plug in what they're equal to right here. So let's do that. My f of x is x squared minus 4. And it's good to throw parentheses on here so you make sure you do the correct order of operations. And my g of x is x squared plus x plus 3. So x squared plus x plus 3. Just plugging in what my functions are defined as. So now we have this expression. We want to simplify this. So let's remove our parentheses and combine the like terms. So plus x squared plus x plus 3. And so I have like terms here, these x squareds, and these constant terms here. So let's simplify those. X squared plus x squared, I'm going to have 2x squared with this x here plus x, nothing to combine that with. And then I have minus 4 and plus 3, so that's going to give me minus 1, right? Okay, now why don't we do f minus g of x. So let's go to a new page. I want to do f minus g of x, which remember just equals f of x minus g of x. And so, again, I just want to plug in what I have. So my f of x was x squared minus 4. X squared minus 4. We'll throw on parentheses again. It is important here because we're subtracting. Minus my g of x, which was x squared plus x plus 3. Plus x plus 3. So now, removing parentheses and combining like terms, this first part stays the same, but I want to distribute this minus sign to all of these terms because I'm subtracting this whole expression here. So make sure that you do that. So you'll have minus x squared, minus x, and minus 3. So they all become minus. Let's combine our like terms again. X squared, my x squared here, and then I also have this minus 4 and a minus 3. So now, x squared minus x squared, those are actually going to cancel out. I still have this minus x, and I need to combine my minus 4 and my minus 3, so that's going to give me minus 7. So in this example, both our f and g were quadratic equations, which means that both of their domains were all real numbers. So we didn't really have to worry about finding the overlapping domain. But in this next example, let's say we have f of x equals square root x minus 1 and g of x is equal to x minus 3. So now we have this square root, and we're going to need to take a closer look at the domains of our functions. So let's do that first. Domains. So note that f of x has a square root. And remember, we're not allowed to square root negative numbers. So that means that I need whatever's inside the square root to always be either 0 or positive. So that means that I need my x minus 1 to be greater than or equal to 0. And solving this will give us the domain of our f of x. So luckily this one's pretty easy to solve. We just have to add the 1 to both sides. And we'll have x is greater than or equal to 1. So that's our domain for f. Looking at g, g is just a linear function, right? So the domain of a linear function is all real numbers. So if I draw my number line, this is the real line, it's the real number symbol. With g, I get this whole thing. But with f, I can only take x is greater than or equal to 1. So let's say this is 0 and 1 is right here. With f, I'm allowed to plug in 1, and then everything greater than that. So the overlapping domain is this part. So the domain that I want to be looking at is this x is greater than or equal to 1. So now why don't we take a look at finding f times g of x and f divided by g of x. Let's make a new page. So f times g of x is just equal to f of x times g of x. So again, I'll just plug in whatever I have for my functions. So square root of x minus 1 and x minus 3. So square root x minus 1 and x minus 3. And so because of the square root, there's not a whole lot to simplify here. I would probably just rewrite it like this, x minus 3 first, and then have your root over here. But this would be a perfectly fine answer as well. So not too much to see there, but let's take a look at the quotient of f and g, f over g of x. And so that's equal to f of x over g of x. So now I've introduced this fraction with a denominator, and I don't want my denominator to be equal to 0. So let's plug in first what we have for f and g. And now because of that fraction, I need my x minus 3 to not be 0. So it adds another restriction to our domain here. So you want to think about what value of x is going to make this equal to 0. And we've done some of these examples before. So if I set that equal to 0, the value x equals 3 is going to cause me to divide by 0. So in this case, I need, first of all, x to be greater than or equal to 1, and I need x to not be equal to 3. Because that was in my domain originally, right? I had this number line. I had everything including 1 and bigger. But now I have to throw out 3. So if 3's here, I need to cut that out, basically. So for completeness in this previous example here, the f times g of x, you might want to write x must be greater than or equal to 1. Pretty much just if they ask you to state the domain, but like for completeness, this would be your correct answer here. Okay, so now that we've talked about sum, difference, product, and quotient of functions, we want to look at one more thing, the composition of functions. So definition, the composition of f and g is given by f of g, that's how this is pronounced, f of g of x equals f evaluated at g of x. So you're plugging in your g of x function into the f function. And the domain gets even a little bit weirder here. The domain of f of g is the set of all x such that g of x is in the domain of f. So you're basically looking at the range of g, the set of outputs, and you're looking at that to see which of those you're allowed to plug into f. And there was kind of a good picture in your textbook about how this works. So you have a set, this is the domain of g, and we'll put a little point in here, x. And then the function g takes me to a set of outputs, g of x. And then from there, you're applying your function f, and that takes you to another set, f of g of x. And so composition of functions just takes you there. It's like applying two different functions at the same time. This is f of g, like of x, I guess you would say. And this set here is the domain of f and the range of g. Like combining the range of g and the domain of f. So why don't we now take a look at an example of what finding compositions of functions looks like. So let's say we have f of x equals x squared minus 2 and g of x equals x plus 1. And we want to find f of g of x and g of f of x. So first thing to notice would be the domains of these functions. This is a quadratic and this is a linear function, a line. So both of those have the domain all real numbers. And so that means that I don't have to worry about what I'm allowed to plug in, right? So with that, we can just begin. F of g of x equals f of g of x, or evaluated at g of x. So like I said before, you take your g of x, the whole function, and you plug it in to your f of x. So that means wherever I have an x, I'm plugging in this function instead, this g of x. So let's see what that looks like. My f of x is x squared minus 2. So instead of x, I'll write g of x. So g of x squared minus 2 instead of x squared minus 2. So then taking that a step further, we know what g of x is. G of x is x plus 1, so we can plug that in. Minus 2. We'll probably want to simplify this further, so you're going to want to FOIL out this x plus 1. So I'll do a side calculation. I have x plus 1 squared, which is the same as x plus 1 times x plus 1, right? So you want to do your FOIL, as per usual here. So first, x times x, that gives me x squared. The outer terms, I get plus x. Inner terms, I get plus x again. The last one's plus 1. So this gives me x squared plus 2x plus 1. And that's just simplifying this part here. So we can plug that in here. X squared plus 2x plus 1 minus 2. So then the last thing that I want to do is combine my like terms. This constant term out here, minus 2, will get combined with the plus 1. So I'll end up with x squared plus 2x plus 1 minus 2 minus 1. So now why don't we try to find g of f of x? So g of f of x equals g evaluated at f of x. So that means I look at my g, and wherever I have x, I plug in f of x instead. So my g of x was x plus 1. So instead of x plus 1, I now have f of x plus 1. But again, let's take it a step further. I know what f of x is. F of x is x squared minus 2. So instead of f of x, I'll have x squared minus 2, and then this plus 1 stays. We'll simplify this a little bit further. Nothing to FOIL out here. X squared minus 2. Remember, you only FOIL if you have a squared or an exponent on the outside. So I just have x squared minus 2 plus 1. Combining my like terms, minus 2 plus 1. I'll end up with x squared minus 1 Now notice, that's not the same as what we got for f of g of x, right? F of g of x was x squared plus 2x minus 1. G of f was just x squared minus 1. So it's good to notice. F of g is not the same as g of f. So the order that you apply your functions in matters, is what that's saying. So why don't we next take a look at an example that has a less straightforward domain. So again, the first thing to keep in mind is that square root. So just have it in the back of your mind when we're solving for the domain. But first, let's just find f of g of x. So again, f of g of x is f evaluated at g of x. And be careful to keep the order straight. F of g is f evaluated at g. And so I look at my f function, and wherever I have an x, I plug in g of x instead. So my f is square root x, but instead of square root x, I'll have square root g of x. Take it another step. My g of x is 9 minus x squared. Okay, so that right here, this is my f of g. So now we want to find the domain of this thing. So we had it in our head that we have a square root. We're not allowed to square root negative numbers, so I need whatever's in here to be positive or 0. So I need this to be true. I need my 9 minus x squared to be greater than or equal to 0. And so we've done some problems like this before. We found critical numbers, we constructed test intervals, and we tested them to see if it's positive or negative on those intervals, but I kind of want to show you guys a slightly different way of doing it. So let me copy that equation over. 9 minus x squared greater than or equal to 0. I think that was it, right? Yeah. Okay, so first, let's still find our critical points. Or critical numbers, I think we called them in this class. And we do that by setting our expression equal to 0. So set 9 minus x squared equal to 0. So we can factor this left-hand side. Nine minus x squared, so that's what we call a difference of squares. So you just take square root of this one and square root of that one. And then one of your factors will be 3 plus x, and the other will be 3 minus x. So like, yeah, remember difference of squares formula. Of squares. Where you have something like a squared minus b squared equals a plus b, a minus b is how that factors. So that's what we have here. We're setting that equal to 0. So then, like we've done before, split this up into two separate equations and solve each of those equal to 0. So 3 plus x equals 0. And then 3 minus x equals 0. So to solve for x, in this one I want to minus my 3 over. Cancels on this side, right? So I have x and I have equals negative 3 here. And then probably easiest way on this side, just add your x to the other side. So then you get 3 equals x, or in other words, x equals 3. So your two critical values, critical numbers, are x equals 3 and minus 3. Okay, so now that we have those, let's take a look at our number line again. Let's put 0 here. We'll put our critical numbers on here, 3 and negative 3. So like plot critical numbers on the line. So let's go back to our other page for 1 second here. I set this equation equal to 0, and I found these to be the numbers that satisfy that, right? So that means that my equation is equal to 0 at those numbers. Now, a few lectures ago, we talked about determining what a graph looks like based on its degree and its sign. So let me refresh your memory on that. Our degree here is 2, right? Because my equation is 9 minus x squared. So the degree is 2. It's even. And then the sign on the leading coefficient, the sign is negative, right? So hopefully you have it in your notes somewhere, but that means that my graph looks something like this, right? But I know what these values are. I solved for them already. They're negative 3 and 3. So I know that this quadratic has to look like this. And then using this, it's kind of easier to tell where your function is positive and negative, right? So over here, I'm below the axis, so that means I'm negative. Here I'm positive because I'm above this axis. And here I'm negative again. So then, what were we looking for? We wanted this thing to be positive, right? We wanted it to be greater than or equal to 0 because I'm taking the square root of it, right? Let's see if I can find that. Yeah, here. I wanted this to be greater than or equal to 0. So that's going to be this region here. So wanted so it's kind of easier to see that the interval that happens is negative 3 to 3. So that's your domain of this f of g. So if that didn't make a lot of sense, you can always do the other method that we know, which was basically the same thing, but you're just plotting your intervals and you're picking a test point in each of these intervals to test whether your function is positive or negative. And if you do that, you'll get the same thing. This method gets a little bit more complicated if you have a higher degree than 2, like if you had a cubic or a fourth power, because factoring it will become more difficult. You'll have more critical points, critical numbers to plot on this line, but for a quadratic, this works pretty well. So the last thing that I want to discuss today is how to identify a composite function. When you're given some function, like how do I know that it's two functions composed with each other? And one of these always shows up on the final, so this is always good to know how to do. So our example here is find two functions f and g such that g of f equals square root of 1 over x minus 7. And we're not allowed to have g of x equal to x nor f of x equal to x, because that just makes it like too easy to do. So we want you to find two different functions so that when I compose them, I'll get this. So first thing, like note the order that you're composing your functions, because as we saw before, the order does matter. So I have here g of f, which is g evaluated at f of x, right? So I want my g to be like sort of the outer function and my f to be sort of the inner function. So why don't we just call this inner part my f of x. So let's let f of x equal 1 over x minus 7. So we're just take whatever's inside. Then we have that f of x is not equal to x, so that's fine. So then let's plug that in and see what we get. So plug this in. So instead of 1 over x minus 7, let's plug in f of x. So then I'm going to have square root of f of x, right? So then you can kind of see what you need your g to be. I'm plugging in f of x into a square root. So I'm plugging in f of x into g, which I want to be a square root. Hopefully you can see. So let's let g of x equal the square root of x. And just the square root of x, not the square root of 1 over x minus 7, because that's what I let my f be. And I just want to plug in f of x where I have an x in g. So let's compose these and make sure that I get the correct thing. So I said that my f of x was 1 over x minus 7, and my g of x was square root of x. So then my g of f of x is g evaluated at f of x. So g, wherever I have an x, I'll plug in f of x instead, square root of f of x. Take it a step further. I know what f of x is. I'll plug it in. 1 over x minus 7. So we did get the correct answer, right? So this part was kind of like checking work. But hopefully the process made sense before that too. Note the order, like note what you're plugging into which function. Set f to be the inside one, and then from there figure out what your g has to be. And with problems like these, there's more than one right answer most of the time. So let's just look at our function one more time. 1 over x minus 7. So maybe I just want this part to be my f. It's a little bit less straightforward this way, but maybe if you see it like that, like maybe this way makes more sense. So if I let my f of x equal x minus 7, then what does this become? Well, this becomes the square root of 1 over f of x, right? So then I want to find the g such that if I plug in f of x, if I evaluate this g of f of x, I'll get this. So then you can kind of see that, well, if I let my f equal that, I need my g of x to be not just square root x, but square root of 1 over x now. Because now you can see if I evaluate this g of f of x, I'll get 1 over f of x, which will give me 1 over x minus 7. I kind of went through that one quickly, but if you're not convinced, maybe try showing it yourself. Like calculate your g of f and see that it works. And yeah, just keep in mind that there is more than one correct answer to these types of problems. Alright, and then this will be the last example that I do today. This is another problem that I pulled from one of the past finals. Find f and g such that f of g equals 1 over x to the 4th plus 10, with your f of x not equal to x and g of x not equal to x. So it's just another example of the thing that we did before. So once again, note the order first. So this time I have f of g instead of g of f, right? So f of g of x is f evaluated at g of x. So again, let's choose our inside function. Let how do I explain it? Let inner function here, inner, be whatever inner kind of function you can find here. So I would pick like this, be inner. So let's let my inner one this time is g. So let g of x equal x to the 4th plus 10. So next I want to plug that in. So now my f of g becomes 1 over g of x. And so now I know exactly what my f has to be. My f of x has to be something where if I plug in g of x, I end up with this. So the only way that that happens is f of x equals 1 over x. Okay, so we'll go through and check our work one more time. Check. My f of x was 1 over x, and my g of x was x to the 4th plus 10. Right? So we'll check. Yes. Alright, so let's calculate f of g of x. F of g of x is f evaluated at g of x, which means I look at my f. Wherever I have x, I'll plug in g of x instead. So 1 over g of x. Take it a step further, I know what my g of x is. 1 over x to the 4th plus 10, which is what we wanted to end up with. So that's how you know you did it correctly.